ASK Aviation School.
The air surrounding an aircraft is constantly in motion. Pressure, temperature, and density change by the minute, driven by weather, seasons, and solar activity. To navigate this, the aerospace industry relies on a fixed standard, the International Standard Atmosphere, or EASA. If engineers tested aircraft in random weather conditions, the resulting performance data would be meaningless. There would be no way to calibrate a barometric altimeter reliably or compare two different airframes. The EASA ignores real-time weather entirely, operating as a rigid, hypothetical mathematical model to create an unmoving baseline for global flight. The foundation for this model was laid in the 1920s as early aviation rapidly expanded. Engineers realized they needed a uniform way to measure performance, leading to the creation of early regional models that were eventually unified. Today, this model serves as the ultimate common denominator. It allows engineers to standardize flight testing and pilots to calculate exact aircraft capabilities, regardless of where they are operating on Earth. Every calculation in the EASA begins at an altitude of 0. This is mean sea level, and the values assigned here define what the industry calls a standard day. This matrix displays the primary sea level constants that pilot candidates must commit to memory. The two most critical variables are a base temperature of 15 degrees Celsius and a standard pressure of 1,013.25 hectopascals. We also have a standard sea level density of 1.2250 kilograms per cubic meter. It is crucial to verify which unit system your charts use, as older aircraft manuals often rely on U.S. customary units rather than standard metric values. To make the physics mathematically workable, the EASA treats the air as a perfect gas. It assumes exactly 0% humidity, meaning the air is perfectly dry. In reality, the atmosphere always contains some water vapor. Because water molecules are lighter than the nitrogen and oxygen they displace, humidity decreases overall air density. As a result, aircraft in actual conditions will almost always underperform the mathematically perfect standard chart. As an aircraft climbs, the air gets colder. In the standard model, this decrease follows a strict linear gradient known as a lapse rate. This graph maps that exact relationship. Scientifically, the temperature drops by 6.5 degrees Celsius for every 1,000 meters you ascend. For aviation altimetry, pilots use the approximation of a 2.0 degrees Celsius drop per 1,000 feet. Starting at sea level, the temperature falls steadily throughout the lowest layer of the atmosphere, the troposphere. This linear cooling continues until we reach a boundary layer known as the tropopause, at exactly 36,000 feet. Here, we hit the tropopause kink. The temperature stops falling and locks into a constant negative 56.5 degrees Celsius. This vertical section is an isothermal layer. Because the temperature is stable, it creates an optimal environment for high-altitude commercial jets cruising near the speed of sound. While temperature decreases in a straight line, pressure behaves differently. Air pressure is dictated by the hydrostatic equation. It is literally the physical weight of the air column pressing down from above. Because air is a gas, it is compressible. This chart demonstrates how the pressure drop is not linear, but exponential. The air is thickest near the surface, and pressure decays rapidly at first, then flattens out as you climb into the thinner atmosphere. However, in the lower atmosphere, we can extract a highly reliable linear rule. For every 30 feet you gain in altitude, the pressure drops by exactly 1 atpascal. A cockpit pressure altimeter functions as a barometer, calibrated to translate these specific atmospheric pressure changes into a display of vertical height. To see how these constants apply in the cockpit, let's look at a standard calculation. We are on the ground at a high-elevation airport on a hot day. The physical elevation is 5,000 feet, the local altimeter setting is 1,003 hectopascals, and the outside air temperature is a blistering 30 degrees Celsius. Step 1 is to calculate pressure altitude. We find the difference between our standard sea level pressure of 1,013 and our local pressure of 1,003. That gives us a 10 hectopascal difference. Next, we apply the low altitude pressure lapse rate, multiplying that 10 hectopascals by 30 feet. This gives us 300 feet of pressure deviation. We add that to our physical field elevation. Our pressure altitude is 5,300 feet. Step 2 is calculating what the EASA temperature should be at this altitude. We take our 15-degree standard, subtract the 2 degrees per 1,000 feet lapse rate, and find that the textbook temperature at 5,300 feet should be 4.4 degrees Celsius. Step 3 determines our EASA deviation. We compare our actual 30-degree temperature to the 4.4 degree standard. The air is 25.6 degrees hotter than the mathematical model. Finally, step 4. We calculate density altitude by taking our pressure altitude and applying the standard density correction factor of 120 feet for every degree of temperature deviation. Adding that penalty pushes our density altitude to 8,372 feet. The hot air molecules have expanded so far apart that the density of the air around the aircraft is drastically reduced. The wings have less mass to push against to generate lift, and the engines have less oxygen to burn for thrust. The wheels of the aircraft are sitting on pavement at 5,000 feet, but aerodynamically, the airframe is behaving as if it is struggling to fly at nearly 8,400 feet. This scenario is what aviators refer to as an EASA plus condition, where the actual temperature is warmer than standard. Operating in these environments severely degrades aerodynamic capability, choking mass airflow through jet turbines and stripping efficiency from propeller blades. Thin air also incurs a true airspeed penalty. Because there is less air resistance, maintaining a specific indicated airspeed requires the aircraft to physically move much faster through the air mass, leading to higher ground speeds and longer stopping distances. A standard rule of thumb for these conditions dictates that every 10 degrees Celsius increase above the EASA baseline will increase your required takeoff ground roll by approximately 10%. In the cockpit of modern commercial aircraft, crews rarely map out these formulas by hand. Instead, the heavy mathematical lifting is handled by the Air Data Computer, or ADC. The ADC continuously ingests raw pitot pressure, static pressure, and total air temperature. By rapidly applying the EASA mathematical algorithms to this data, it outputs precise, real-time calculations for pressure altitude, true airspeed, and Mach number directly to the displays. But automation does not replace comprehension. A professional pilot must thoroughly grasp the underlying lap rates and density logic to instantly recognize when a clogged static port or an iced temperature probe is feeding the computer fatal errors. To pass commercial certification and command these systems, the mathematical structure of the atmosphere must be second nature. Mean sea level is always anchored at 15 degrees Celsius and 1,013.25 hectopascals. In the troposphere, temperature drops by 2.0 degrees Celsius every 1,000 feet, and pressure drops by 1 hectopascal every 30 feet. The tropopause begins precisely at 11,000 meters, roughly 36,000 feet, locking into an isothermal layer at a constant negative 56.5 degrees. Because the local speed of sound is dictated entirely by temperature, this stable layer provides the necessary predictable envelope for high-speed Mach operations. And regardless of where you are or what the altimeter indicates, density altitude is the final, uncompromising dictator of physical aircraft capability. Mastering these constants and calculations allows a pilot to navigate a volatile atmosphere using a structured mathematical grid. This standardization provides the shared language necessary for safe global aviation.
ASK Aviation School.